Today we shall be talking about work from the physics concept. Because when we say I'm going to work, it means a lot of things. A student going to work means they are going to school to do some school work. I'm going to do my homework, which involves reading, doing summary, solving something. It could even be to recite a poem to learn it or anything like that. Or a doctor saying I'm going to work means hospital, patients, treatment, surgeon, cutting up people, a farmer going to take care of plants or animals or anything like that. So the concept of work is really broad, it's really relative to a lot of things. But today we are looking at the meaning of work when it comes to physics. In physics, when we say work has been done, what do we mean? So in physics, we say that work is said to be done. Work is said to be done when a force moves a body through a distance in the direction of force. So this is the physics definition of work. In physics, when we say work has been done, we mean that a force has moved a body through a distance which is in the direction of that applied force. So when I have this object and I move it from this point to this point, according to physics definition, I've done some work because I've moved a body through a certain distance and it was in the direction of this applied force. The force came from me and it has moved this body through this distance. So that is what we mean by work in physics. If there is no meaning that, okay, conditions must be met, is that there must be an applied force, there must be a movement of a body from one point to another, and the direction of that motion must be in the direction of that applied force. So those are the conditions. So now, if this object is just staying here, no force is applied, no motion is taking place, of course we know no work has been done. If this object was lifted, maybe this is a heavy object and somebody is just carrying it, standing on a stationary position, according to physics definition, this person has not done any work because this object is just stationary. There is no motion. Yes, the person is sweating, the person is tired, the person is just frustrated at that point, but according to physics definition, no work has been done because the force used in carrying this load is not moving this object to any point. Okay, let's say this is also a heavy object and then someone is pushing it, but there is no motion. So in this case, there is an applied force. There is a pushing force or a pulling force. Yet, this object is not moving from any point. It's not budging. It's not moving anywhere. So applied force is there, but there is no displacement of this object through any distance. So no work has been done in that case. Stationary, no work is done. Whether you are carrying something stationary or you're pushing something, yet the force was not enough to move it. In physics definition, work has not been done. Work is only done when an applied force moves a body through a distance in the direction of that applied force. That being said, we can see that work is equal to force times distance. The applied force times the distance this force moves the body. So that's just the basic formula for work, force times distance, and its SI unit is joules. So we say 1 joule, 2 joules, 3 joules, that's the amount of work done. Work is measured in joules. Now, could there be a case whereby an object is being moved through a certain distance by the application of the force, but the distance is not in the direction of that force? Well, yes, there is a case like that. Let's say we have a body, resting on the horizontal floor. This is a box resting on a horizontal floor, and then someone is pulling it. So this is the force. Someone maybe tied a rope to it, the person is dragging it, the person is this tall person dragging it on this direction. And then you see that this box is moving in this direction. Did you see that? So a force is applied in this direction, yet this box is moving in this other direction. So in that case, we are going to look at the angle of inclination of that force. So in this case, what we are going to do is we are going to say that work is equal to this force times the cosine of this angle of inclination to the horizontal times this distance moved by the box. So this is just to get the horizontal component of the force, okay, which I don't want to bother you with. So we say, or simply we can say that work in this case is equal to F d cos theta. So it's just concise. Force times distance cos the angle of inclination between that force and the direction of motion of the object. Okay, now let's also say that we dropped an object through a certain height, or we lifted an object through a certain height. In that case, we are dealing with gravity. When we are moving it up, we are working against gravity. When we are moving it down, we are going according to gravity. So in that case, the force, when we are lifting something, we are working against the force of gravity. When we are dropping it, like a fruit just falling from a tree, yes, it moved through a certain distance, and it was actually the force of gravity that moved it. So some work was done by that fruit. Some work was done on that fruit by the force of gravity. So in that case, what we say is that work is equal to the weight, which is mass times acceleration due to gravity, times that distance. The distance in this case is a vertical distance, which we can call height. So when we say that we lifted something up or we left something to drop down, the formula we use for solving for the work done on that object is the weight, which is mass times acceleration due to gravity. That is a force. Weight is a force. The pull of gravity on an object times the height, which is the distance. So we can see in any of the cases that basically work is equal to force times distance. Okay, we are going to solve some examples. So example 1, we have that a force of 50 Newton. Let's be writing out our parameters as we are seeing them. The force is equal to 50 Newton. It's used to pull a box of 80 kg. So this is the mass of the box, 80 kilogram, along a horizontal floor. The work done after a distance of 3 meters is what? So we are looking for work done. You don't know the work done. Then we have the distance moved, which is 3 meters. Now remember, we said that work done is equal to force times distance. So we have work done that we are looking for is equal to the force times this distance. In this case, this mass, we don't use it. Sometimes in a question, you're giving some parameters in which you don't use. Please don't be tempted to use it. Just go according to the formula of what you're looking for. So we substitute. Force is 50. The distance is 3. 50 times 3, which is 150. So the work is equal to 150, and the SI unit of work is joules. So the work done in moving this box through that distance is equal to 150 joules. You can see how simple that is. Just stick to the formula. Okay, number 2. We say a stone of mass m kg is held h meters above the floor for 50 seconds. The work done in joules over the period is what? And then we have all these options: mh, mgh over 50, and then the d part is 0. So let's look at this objectively. We say that we have a mass m kg, we have a height above the floor and is held there for 50 seconds. So they're asking us for work done. Now remember, from definition of work done, we say that work is said to be done when a force moves an object through a certain distance in direction of force. So this thing, it says that the stone of mass is held above the ground, above the floor, for 50 seconds. So there was no motion, it was just stationary on that top. So work was not done. Do you understand? There was no motion, there is no movement. Yes, there was a height, but it didn't go through that height. That object did not move up or down that certain height. So in this case, we say that D is the answer. It is zero work done. Energy is there. When we talk about energy, energy is there, but no work was done because that object was not moved through any distance. It was just stationary for 50 seconds. So no work was done. The work done in joules for that period is 0. Why? Because there was no motion of that object. The force was not able to move the object through any distance. Okay. Number 3, a load is pulled 5 meters along a horizontal floor by a constant force of 20 Newton, which acts at 30 degrees to the floor. Calculate the work done by the force. We start by writing out our parameters. So pulled 5 meters along a horizontal floor, so that's a distance. We say that the distance is 5 meters by a constant force of 20 Newton. So we have that our force is 20 Newton, which acts at 30 degrees to the floor. So this force is inclined at 30 degrees to the horizontal floor. So we have that the angle of inclination is 30 degrees. We have to calculate the work done. So we said that work done for forces that are inclined at a certain angle to the horizontal is equal to FD cos theta. We remember, right? Okay, so we substitute. F is 20 times 5, which is the distance, and then times cos of the angle theta, which is 30 degrees. 20 times 5, that is 100 cos 30. And then when we use our calculator, we have that it is 86.6 and the unit of work is joules. So the work done by this force is 86.6 joules. Then we look at this other example. A load of mass 80 kg fell down from the floor of a lorry which is 2 meters high. Calculate the work done by gravity on the road, and we are to take acceleration due to gravity G as 10 meters per second square. So we write out our parameters. We have that the mass of this load is 80 kilogram, fell down from the floor of a lorry which is 2 meters high. So the lorry, okay, so the height is 2 meters. So we have to calculate the work done, and we are given that G is equal to 10 meters per second squared, and then the work done is what we are to look for. So we said that when we are lifting something up through a certain height, vertical height, or we are dropping something down through a certain vertical height, we now say that the work done is equal to the force of the weight, which is mg, times that vertical height. So we have that work done for that case is mgh. So we substitute our values. M is 80, G is 10, the height is 2. 80 times 10, that's 800. 800 times 2, that is 1600. That is 1600 joules. We can see that work done is an easy thing to solve. Just remember the formula for the 3 cases of the work done. Now let's talk about force distance or force displacement graphs. So in physics, whenever you see a certain quantity stroke another one. That means this first one is for the vertical axis and then the second one is for the horizontal axis. So force displacement or force distance graph is basically a graph that has force on the vertical axis, and force is in Newton, and then the distance or displacement is in meters or centimeters or millimeters. They will give you the unit as the case may be. So this is a force distance or displacement graph. So whether it's distance, displacement, they are still same units. Okay, so for force distance graphs is just all about is a plot of work, and for force to be here and then distance is here, we can get work done from a force distance graph by getting the area under the graph. So the graph could go this way, then we have a certain force here, we have a certain distance here. So for this case, we are saying that the area under this graph is equal to the work done. So we can see that the shape under this graph is a triangle, so we can say half base times height. If the graph was this way, a constant force over a long period of time, we can see the area under the graph. We can say that it is just a rectangle, which is just length times width. So the force times the distance given. So let's delve into examples and then see how to use them. The diagram below illustrates a force distance graph for the motion of a wooden block. Determine the work done on the block when moved through a distance of 5 meters. Okay, so we can see from the graph that a constant force was applied over this period of time till this distance in meters was up to 5. So we can see the area under this graph is what we are looking for when we say work done. That is the force times distance. That's this force, this distance, this height times the length. Okay, so we can see it's a force of 20 Newton. We can see that the force is 20 Newton. And then we can see that the distance is equal to 5. So the work done, which is FD, is equal to 20 times 5, which is 100 joules. We can see it's very, very easy. Once you're given a graph, you don't need to fret. All you just do is the area under the graph is equal to the work done. So far it's a force distance or displacement or even extension graph. Okay, so let's solve the second example. Using a force displacement diagram shown below, calculate the work done. So we can see the load in Newton. The load is also a force, that's kind of a weight. And then we can see an extension. Extension is also a distance, an extension. Distance. So we can see it's in cm, so we have to convert to SI unit, which is meters. So we can see that the area under the graph, you can see it's a graph going this way. So the area under this line of the graph is a triangle. So we can say that the work done will now be half base, and the base we can see is 1 cm, right? 1 cm, it's in cm, so we have to divide by 100 to get it to be meters, times the height. We can see that the height, do you see, we trace it, is 4. So we have that 1/2 of this, so we have it to be 0.02 joules at the end of the day. 0.02 joules. That is half of 4 is 2, and then 2/100 is 0.02 joules. It's just for you to see the shape of the graph and then take note of the units, especially of the distance area. If it's in millimeters, you divide by 1000. If it's in centimeter, you divide by 100. Okay, so finally, let's look at this strange graph. So we have it that a body is under the action of a force F, such that the force displacement graph of the body is semicircular. as shown in this diagram. The work done on the body by the force moving through 24 meters is what? Remember, we said that from a force distance graph, it is equal to the area under the graph. So this area we can see is a semicircle. And then the area of a circle is equal to pi r square, right? Good. So pi r square. So the area of a semicircle will be pi r square over 2 because semi is half of a circle. So we now say that's the work done. Okay, let's even look at the circle. Let's get the radius because that's pi is a constant. It's now the radius we need to get. So we can see that this is half of the circle. So this is the diameter. And the diameter is 24, so half of it is 12. Can you also see that this is also 12? Did you see it? So the radius of the circle is 12, both this way and this way. So the radius is equal to 12. So we can say that the radius is equal to 12. So whether it's 12 Newton, that's going vertically this way, or 12 Newton, whether we are going horizontally this way or this way. So you can see it's a circle of radius 12. So we see that work done is equal to pi times r, which is 12, squared. The 12 is squared over 2. So we have it as pi times 12 squared is 144 over 2. So at the end of the day, we have 72. That is half of 144. 72 pi joules. This is actually a JAMB question, so this is how it came out as. So this is all about work. We've looked at the definition of work, the SI units, and some calculations under work, and of course the force, distance, or displacement graphs. So that's all about work. The next we look at energy.